Welcome. This video we're going to do this problem that we've specified here. This is a picture of the Google folder, locally distributed. Go up here and hit the files. Okay, you download these from the Google Drive, and let's start first with the one system mass. Okay, so here is the folder. Essentially, if we just run this code, this will, and put a breakpoint right here. What I'm going to do is I'm going to run each one of these. As you see it, you're going to see the frequency changing. And you'll see as we continue through this, you're going to see the two plots here. Now this peak actually is not as high as it should be. In class we ran it. It actually goes up to 10. But the look of the plot is fine. What we're going to do is I'll even go through the process of how you would place this, or an acceptable way to place this in a printed report. We'll just go in and I will open Microsoft Word. Here's the Word document. I'll move it back and forth between the screens. I will start what is commonly called a snippet tool, and I'll just go in and snip it. Go back to the Word document, right click and hit a paste. There's your, you can resize it however you want. So put the appropriate text around it. It moves back to the other screen. Okay, let's do a new one. Let's do the semi-log plot. Come back over here. Put a space in there. Paste it. Here's your semi-log plot. So what does this answer? Okay. If you go in and look at the final and give it a second to come up, move it across. So the first question is a plot of the response with none of the other masses. So this is what I get. So these the plot you're looking at currently satisfies this requirement. So now I just did that. Okay, now how do I do this? And actually it's not that hard. Go in now. 2 or 3 ways you could do it. In here I'm specifying these 3. But you know from this that if I were to specify, if I specified the mass and then the stiffness, the omega would be the same. The B would change. So now I need to specify B right here. Hang on. I need to specify B such that it equals to, see if I can do this, symbol times 2 m omega n. The 2 and the m and omega n are that. So if I want to specify B, all I do is specify this value. So now I rewrite this in the equation, 2000, and then add a 10 to it. So 20,000 times that gives me B. So let's go back and do that. Okay, so I'll just go down and put a line under it. B is equal to 20,000 times, well, what values did I need to be entering? First, it says I want to know 0.1, 0.01, and 0.001. So let's start with 0.1. The next thing you're going to find, and I will just do this in a straightforward case here. Here's what I'm going to do. I'm going to basically put a plot or a stop right here. Oh, I need to do a control indent so it looks a little bit better. Run this thing. Okay, the first thing you see is that's the case. Very small displacement. But what I'm really interested in is I'm interested in the case where omega simply equals to 10. So I'm going to try this as an experiment. I am going to run up to, say, go ahead and hit F9 here, or since evaluate the selection. Okay, I'm unsure of what omega ended up as. Omega was 10. Let me go see if I can find, there you go. Okay. I think what we'll do is we'll just go back and run this through the whole sequence and see if we have enough definition. In other words, did we go deep enough into time? Save this and run it. It's growing, as you can see, but the damping kept it from growing too fast. Now it's shrinking. You can see the thing shrinking. So here's what you get. Okay, this is the log plot. This is what you get if in fact you put a decent amount of damping. Actually, it's quite a bit of damping there. It's still not over damped. And so in essence, what you should do is you should label these two plots. Go in, use your snippet tool, and I just snip both of them together. Over to your Word. I wouldn't put both of them together like this, but unless you put labels on each one. But what you have here is you have a linear y-axis and a logarithmic y-axis. Makes it look much like a decimal plot. Okay, so then I would go back. Let's move that out of the way. I would go back into the code, change this to 0.01. I believe the smallest one was 0.001, if I'm not mistaken. Yeah, so here's the values: 0.1, 0.01, and 0.001. Let's look at the 0.001 just because it will be the most extreme here. Save it and run it. Of course, there's my spike. I still don't believe my spike reached the complete level. So what I'm going to do is I'm going to run this to 500 and then stop this and look ahead at 400. Save it and run it again. It's going to take a lot longer to run. So I am going to, well, it's not that bad. So here, what you're noticing, the amplitude begins to increase. What we're looking at is the steady state, so the downstream amplitude. You can start to see a beat frequency appearing. It becomes larger and larger. Then you get the large amplitude and it comes back. So eventually reach a point, hopefully this thing will finish soon. So the amplitude is trailing off, and here's our spike. Not too much different than the last, so we'll accept both of these. Let's go ahead, do what we would normally do. Go ahead and grab these two, use the snippet tool, grab those two, come back to your document, and of course you really need to put labels on these. Labels along the X time, labels along the Y would be the displacement. So here you see what happens with have more damping. This is quite a bit less damping, and so I did them out of sequence. So let's go in now and do the last set of damping. I'm just going to minimize these. The last set of damping, which was 0.01. Let's go ahead and just run it for 300, and we'll pick this up at 250 on. We'll save it, run it. So you can see as the frequency comes larger and larger, the amplitude grows until you reach resonance, and then it starts shrinking back. Alright, there's your two plots, 4 and 5, and if you compare the amplitude, they're quite a bit different. Using your snippet tool, you can go out and grab them again. And then you can come back. Now if you wanted to, and this might be something to consider, okay, came back from a pause. I'm somewhat dissatisfied with what I've got with a couple of regards, and here's how I'm going to fix them. I'm going to come back and do it this way. Put a hold on at the end of each one of these plots. I go in and change each one. I'm going to save it. I'm going to drop the breakpoint so we complete the whole code, and we'll just run them through all the way. You see it coming close to resonance there, and then coming away from resonance. Alright, so we have our first answer here now. Hopefully the plot has the hold on it. I'm going to go back and put a 0 in here and run the code again, and let's see what we get here. I'm going to pause the video and we'll come back when it finishes. Okay, here's what I get when it finished. Obviously both plots are together, and I have one more to do, and I put a 0 inside there again, run it again, then we'll go ahead and pause the video and it'll come back. I'll come back when it's done. Alright, so there's my 3 solutions. You can now begin to see why in the different subject matters you've had over the years, you'll end up with a log scale for decibel out here, because if you look at the linear scale, you see that lower one is simply flat, where you do see a little bit of a hump here, so you get to see these a little bit more. Now of course this is not exact, because this point should actually be up here. Each one of these points at resonance are a little bit lower than what they should be, but that's okay for right now. We're just going to go with this. Now I would actually prefer this to be in here than what I've done so far. Now the second thing is I'm somewhat dissatisfied with this, so let me see if I can figure out how to fix it. We'll put it in edit mode, make it full screen, and then if you look over here, you can do a text box. So I can do a text box, or better than that, let's go ahead and delete that. I want to do a text arrow, say to this one, and then what I'll put in here, I believe okay, so what you notice is I typed in the zeta and up came the symbol. Is I can do another one, text box here. Oh nope, sorry, wrong thing. Delete the text arrow, sorry. Put the arrow right here, backslash ZETA. That will invoke the LaTeX interpreter, and hit the button, it comes up, and then text arrow again, ZETA equals to 0.1, and then you can basically hit the, then technically you really do want an axis label, so you might want to put time there, Y label being, you could just put X, that would be fine. You could put a title on here, frequency response, and then go out of the edit mode back into that mode. Here, let's make it no longer full screen. It looks kind of funny that way. Then this looks nice. This is what I would turn in, and I'd probably think that that would be, and now that I see the log Y versus the log Y here versus the linear Y, I don't even think I would even touch or even consider that one. This is what most people are used to. So what I would do is grab this snippet, go in, get a new one, grab this one, go back to your Word document, get rid of all this junk that you had before. Okay, you essentially have nothing, and oh, wait a minute, Control Z, this is the one for the 0.25, so you want to label that one the same way you're labeling this one, and then put that one in there. So this is a nice way to present this. So I would present it this way, and I would put labels on this one as well. I'm just not going to run the video backwards and go do it. So we have now accomplished both this task and this task, so we're done with one. I think from, if you're watching this video, you will listen and know to do this. Skip 2 altogether, because that's kind of a sort of a mutation of something that has some use. It's not very useful. You've seen the plots pass your face as it's constructing the frequency response. I don't need to see that, so forget that and go straight to 3. 3 is kind of interesting in the meat of this whole problem. It is, how do you hang a mass and a spring off of it, given that it's this type of damping, so that you can get that amplitude down. Not exactly the easiest thing to do, but one of the things you've noticed is this gives, what we've done so far gives us a judge, and let me get rid of some of these plots. It gives us a judge for how long in time we need to run this code. But it's a single mass system. It's not a dual mass system. So we need to go back in and look at our two mass system now. Open it. Now I'm gonna head back off to here and place it right there. Save. Alright. I've done some moderately quick changes here, and we're going to I'm going to run them to make sure they're right here first. But this was the initial mass. I'm sorry. This was the initial mass. This is the initial spring, initial damping. So I'm just going to go ahead and go in here and look at these two. Now what happens is I have to construct my mass matrix, my stiffness matrix, and it only, of course, stiffness only deals with the springs. So what I have is I've labeled this one K1, and this one I'll make it tiny, so it's K, make a little bitty mass. So this is the little m and this is the big M. So ask the question to put on the diagonal, this being the diagonal of row 1, what are the springs connected to this? Well, K1 and K2, add them together. The location, which is 1, 2, so you got a stiffness matrix, which we've answered the question of what should go on this one, K1 plus K2. This is what connects. So this one is what are the springs connected between mass 1 and mass 2? Well, it's just only K1, this K right here. This is the same location. These are always the same. And then finally, in this location, what is the sum, numerical sum of all the springs connected to mass 2, which is just simply K. You do the same thing for the damping. So with that, let me go over and get rid of all this stuff. I've only gone to 100 here. I'm not sure that that's all I need to do, but that's what I'm going to do temporarily and just go with it. I'm beginning to think that I want to just comment those out. I don't even want to see the other two figures. I don't want to see figure 4. I want to see everything in a semi-log plot. So as time goes by, I'm beginning to get a feel of that. Let me make sure I've done the problem correctly. Okay, C is equal to 2 zeros and a 5 times K. 2 zeros and a 5 times K. And let's just run it. Oh, it's putting here's my plots, of my two displacements. The displacement of the big mass and the displacement of the tiny mass. And here's what we've gotten. Now, let's think about this for a minute, and let's compare by looking at our Word document. And in our Word document, these are the two situations. In other words, okay, the first one we ran this with the actual values that were specified back here. In other words, 500, 1000, and 100. So these three were exactly the right numerical values that ran on the last one. And now what we have done is we've gone and hung a mass. We've hung a mass. We just arbitrarily specified it, mass of 100, so it's 10 times lighter than the big mass. The stiffness is not very high at all. The damping is proportional, so it's proportional to the spring stiffness, and that's what that's why that is set that way. If I increase the spring stiffness, it'll increase the damping, but I can change the mass around, it won't do anything. But again, let's compare. What we see, and this is the whole point here, what we see is the amplitude without that mass. Actually, it's a little bit higher than that. I think it's close to 10. And if you look at this one, okay, it might be a little bit higher, but even if it is, this plot placed on here, here's 10 to the first, here's 10 to the first. So this thing, just by placing this extra mass hanging, has dropped down to this level. So can I get this peak out of here? You know, make it continue to go down and be flat? That I don't know. And that's what we're about to do, is to see if we can do that. To check myself and to make sure what's entering my mind is I want to see really where this peak is. You know, I'm going to go back to the code and increase the time level. Go back to the code. What I mean by the time level is I'm going to pick here's what I'm going to do is I'm going to say TF for time final, and I'm just going to run it to 400 and make this TF, whoops, wrong sequence, TF, and then make this say 80% of TF. That means I'm only taking the last 80% here. And I'm going to go ahead and run it 400. This will take a few more minutes to run, but I'm going to just hit it and let it run. And I'll actually pause this because you can tell it's crawling along. Yeah, I made this thing crawl along. I'm not sure that I really actually changed it that much. The peak still looks about the same, so I'm guessing that we're okay with it. So I'd say it's okay. It's not perfect. I could probably get this to be smoother, but as you can well see, or here, no, you can't see it now because I put all the red marks on it, but you can see the clip right here. It goes from this point to that point. It should be a little smoother right there. That's a little bit too much detail, but the point remains that if I'm patient enough, and this is the displacement of the little mass. Notice this. I mean, generally the little mass is not bouncing around a whole lot compared to the larger mass. So, but it does take the amplitude down, not so strangely. And of course, what you notice is it's bouncing around at a significantly different frequency than the other one. But in fact, you notice it took that peak down. Let's see if we can figure out what values of K and M we could work on. I mean, I have no idea. You're watching me solve this thing the first time as well. So here's what I'm going to plan to do. Okay, looking back at the code, somebody gives me a problem like this, then what I'm going to do is I'm going to do this. I'm going to sketch on it. I have these values up here. Well, let me move up. Move the code up. Okay. First of all, we have to realize, let me fix this. We have to realize, number one, we saw this plot with a peak. We knew that peak occurred at 10. We're just going to specify 10. In this loop, we're varying the frequency, the forcing frequency, from 8 to 13. We don't need this loop to optimize the best value of these two values. What we really need to do is we need to put K on this axis, put M on this axis, and put a mesh grid across here. In other words, put a mesh across here and specify a bunch of values. I don't know. Let's start with, 50, say 100. I mean, I really don't know. 150, so on and so forth out here. K, what should K be? I don't know. 10, or say let's start at 50, 100. And what we'll do is the height of this grid, each one of these points will be the displacement at a forcing frequency of 10. So with that in mind, that gives us an approach. So what we need is we need to specify this. We need a loop that starts here and goes over and includes this with a forcing function of 8, and it loops twice, once over M and once over K, until we determine the height of each one of these intersection points and we build a surface. So let's go in here and do this. Get rid of the pen. And so I'm not sure the best place to do it, so I'm going to leave this part of the code here. And what I'll do is interject the loops right here. Here's the way I'm going to do this. Actually, I need to back up one and interject the loops right here. What I will do, okay, these are specified, so I'm going to put a double percent there, so it'll isolate those. And then I'll say something like loops. Do it like that. And then I'm going to say M is equal to, I have no earthly idea, so 400. And then I'm going to do the same thing for the stiffness. I don't know. Once I have it, I'm going to do a copy and a paste. But what I'm going to do is I'm going to do this. M1, K1, forward. M is equal to M1, and forward. K is equal to K1. And I'll go down here. I need to take this, put it right before here, and temporarily what I'm going to do is this. I'm going to select everything, right click and smart indent so I can see it helps me line up the code. So I need to also specify that the frequency has to be 10. And I'm also going to say that my time frequency, copy that out, put that back up here. I really don't need all of this, but here's the way I'm going to do it. Go ahead and put this, smart indent it again, but this time I need INDX equal to 0, and I need JNDX equal to 0. Now, if I'm going to do a mesh grid, I'm going to need the particular values. Now this I may take a little bit of time doing. So here's the way I'm going to approach it. I'm going to stop the code or do breakpoints and make sure I'm doing it correctly. So I'm going to run down to here. I've got K's, I've got an M. Now let me do this. Okay. And I'm just playing right now. So M1, K1. Now let's see what that produces. If I hit this and hit the evaluate the selection, I've got that. Now what I have is repeats, so if I look across this, I see 100 several times, and I look across this, I see 100 vertically. So this will actually give me my mesh grid, but that's not very useful for a loop. However, if you look at this, this is the number of times we will actually run through this loop. So, in other words, we will hold it at 50, and then we will go through a loop. But this one, so every time I circle, I'm circling one here. So I'm doing this, and then this one, this and this value together, this and this value together, this and this value together. So my goal here is to loop through all these particular combinations, everything on here. So I've got 1, 2, 3, 4, 6, 7, 8. 6, 7, 8. So I've got 64 different combinations. And that may be enough times to run this thing. So my initial thought here is to approach this slightly different. Since in fact the size of M and the size of K will always be the same, even if I do something like this and evaluate the selection, what you'll see is K and M will always be the same size regardless of any individual size here, and we'll just hold it that way to begin with. What I'm going to do is I'm going to do this. I'm going to say forward I is equal to 1, 2, the size of, you can choose either one, M or K. M, and I better use another index besides this. So I better use, instead of M and K, maybe I'll say this and that to tag them. Size of M, the first index, K is equal to size of M, second index. Now let's double check this. If I select that, what is that? Oh, I haven't specified it yet. Now let's look at it. It's 10 by 8. Makes sense. I no longer need these. Now I need to put in M. I don't need to put in that value. What I do need to put in is M is equal to the M with a little bar under it. And I don't know why I called this K. I wanted to make it J. Now what I'm making sure of is my first index is the I, because that's the first index, the location here. Then K is equal to, and this should go through the code. Now here's what my whole goal was to do. I comma J equal to the maximum of the Y logical. I believe that we're okay. Now here's what I'm going to do is I'm going to reduce this considerably just to get some values out of it. Whoop, let's go down to even 200. Let's stop the code right there. There's M1, there's K1. So we're looking at a 4x4. We're going to do this loop that many times. So I'm going to continue. And define variable K. Oh, that's very simply because it isn't defined yet. There. Run it again. Undefined variable index. I don't need the index anymore. Now, unfortunately, instead of doing it that way, let's do it like this because I don't want it to just go wild on me. Okay. I solved the ODE. My X value, 1 by 1, was that. In here, let's say the ODE for 5. Yes, I didn't go in and put any, I put no values or no functions in there. The code you have currently or downloadable does have those in it. I'll go in and extract those. So let's do this, continue. Okay, so what we have is we should have two values. I'm going to take this completely off and let's just let it run through. Right now it's busily running through its solutions. It's not giving me any response, so I think I better put a print statement just so that I get the feeling that everything is going okay with it. Okay, but I finish. Nope, I did not finish yet. Okay, now I did. So there is my deflections. And obviously I need to reach out further, but at this particular point, if I decided to just type in surf and type in M, K, and X, I'll get a surface somewhere. I don't know, that's definitely not it. I'm looking through my plot list. That's not it. There it is. Okay, so there's my surface. So it looks like not much difference. So what I need to do, just for my own observation, is this. I want to put a list so I can watch the thing go through so that you're not left in the dark. And then we'll put I'm going to run it again just to see if that will give me some indication so I can watch the thing go through. Oh, yeah, let's break it because put those suppressions of output. Okay, so now you can watch it go through the solution and watch it index itself through the whole thing. And almost done and done. So I think what I'll do now is I'll go ahead and add this as a line of code. If I evaluate that selection, I get the same plot again. So what I'm going to do is I'm going to open this up to a larger set of values, but before I do that, I'll look back at my plot and see which ones were which. Okay, here I need to go ahead and say, okay, X label, because it's hard to determine otherwise. X label would be the mass, Y label would be the stiffness, then Z label say the amplitude. Let's just make sure, because hit that, right click and evaluate the selection. Wrong item. Let's go back, look at my figure. Looks to me as if I were really looking for a minimum value, maybe, although there's not too much difference between these two, running a stiffness and a mass up around 200. So what I'm going to do is, but then again you got another one over here that's low as well, and that's with a mass of 50 and a stiffness of 200. So really I should have put a limit on where I should have gone here. So I'm going to go back and look at this, and I think instead of finding the minimum, just the act of going through and finding the minimum would probably be sufficient for me for this project. What I'm going to do with the remainder of this code is I'm going to comment it and put a breakpoint there, save the code and run it. It's going to be a very, very long run. So what I'm going to do is pause this and come back when it finishes. Alright, after running through that sequence, which took quite some time, this is the results I obtained. For some reason there's two lower spikes, but there's a very low spike right back here, which that right back here seems to decline around the mass of 10 and the stiffness tending to increase. So the question is where should I stick my efforts at? And it's pretty interesting, but if I line it up, this back edge, even with these blips, which I'm a little bit concerned about because it's possible that in fact I didn't allow enough time in the solution for the amplitude to damp out, back here that's not a problem. And you have a valley that's coming at you across this direction, and if you trace that direction out you'll find something interesting. There are two possible locations for a lowering here. If in fact I look at this across the way, I would say if I drew a line up this way and if I continued up this direction, so I keep a mass of 10 and continue to increase the stiffness, what happens? And what happens if I go along a line in which the slope, let's see, hang on. So the slope of this would be the rise of, this would be 10 to, I don't know, 120, so the rise would be about 110. The run would be 200 back to there, roughly 160. I could continue along this slope out here and see if it will get lower here or lower up in this region. I think what I'm going to require you to do is to produce this plot and call it good with this. Let's go ahead and do one more plot to make it complete. And that is this plot. We'll do a figure 1. What was the other figure, by the way? Oh, it's figure 1, so we better do figure 2. And we better, if we're going to do that, we might as well label this one figure 1. Go back in and redo both of these. Hit a evaluate selection. And now you got a contour over here. If you want to see the bars, you can see this. Not too much difference, but you can see the lower part going here and the lower part going there. I think what I want is I want these two plots, and I will consider that to be enough for the project. So, but I will do one more thing in this code here in a second. So first, we'll go over, get this snippet tool, gonna snip the contour here, go back and get the Word document, drop that in there, do another snippet here. I want to snip out this one as well. I want both of those. Go back to your Word document and drop it in there. One of the things I would like to do is I would like to go ahead and trace out the rest of this. What I'm going to do though is stop this video and we'll continue with a second video.